Friction is an important type of force that we see in our world every day, and friction is the reason that most objects come to rest if you just leave them alone. There's friction all over the place that lets us do what we want. Friction enables us to walk, and it lets us it lets us move around our environment. So it's pretty important as far as daily life goes. Um, Friction it's caused by the shape of an object at the molecular level. Objects that are rougher at the molecular level will tend to have greater amounts of friction, and objects that are smoother at the molecular level will tend to have less friction. And what is smooth or rough at the molecular level isn't always obvious based on looking at it. A sheet of paper, for example, looks fairly smooth, but once you get down to a more molecular level, it's fairly rough, and it does have friction. Whereas something like, well, I can't think of an example of something that looks rough, but it is smooth at molecular level. But anyway, and the friction between two objects is primarily dependent on what those materials are and what their shape is, but it's also dependent on the normal force. So friction always acts parallel to the surface whenever two objects are in contact, and it is proportional to normal force. The greater the normal force, the greater the friction. You might have noticed this before in certain contexts. If you rub your hands together, you generate a little bit of heat. That comes from friction. If you push your hands together harder and rub, then you get more heat. There's more friction. And you can see that pretty easily. Like if you push your hand down on your desk and try to move it, that's harder than just resting it on your desk and trying to move it, because that normal force is bigger. Yeah. There are two types of friction. There's kinetic friction and there's static friction. Kinetic is when your object acts when your object is moving, and static acts when your object is at rest. Right? You may have noticed, especially for bigger objects, that you can push a little. If you push on them, but you don't push hard enough, they're not going to move. The reason that happens is because of static friction. When you apply a force, there's a static frictional force that balances that out. Then once you, I don't know if you guys have noticed this either, but it's easier to keep an object moving than it is to get it started moving. It takes more force to start an object moving than it does to keep it moving, and that's related to kinetic and static friction as well. Kinetic friction, which we will typically use the symbol little f sub k, is equal to, this is the Greek letter mu sub k times normal force. Mu is the coefficient of friction, coefficient of friction. Mu k is the coefficient of kinetic friction. Mu s is the coefficient of static friction. And like I said, that has to do with the shapes of the objects at the molecular level. This is interesting because it is always constant. Once an object is moving, the kinetic friction doesn't change. Now you'd think that you would get, it doesn't have to do with surface area at all, which is interesting because you'd think that if you have more area touching the ground, you'd have more friction. But that is not the case. It also doesn't have, it isn't really related to velocity at all, even though you might think that if it's hitting more ground, there's going to be more friction. But it's not dependent on either of those things. It's only dependent on that coefficient and the normal force. Static friction is always, static friction is different because static friction opposes an applied force. So if I try to push my desk sideways, there's a static frictional force that balances out that force that I push with, and then if I let go, then that static frictional force drops back to zero. So static frictional forces greater than or equal to 0, and then it's less than or equal to the coefficient of static friction times normal force. Okay, so the maximum value of static frictional force is mu sub s times normal force. However, the value of the static frictional force isn't always equal to mu sub s times normal force. So be careful of that. For example, let's say we have a desk that has with mass 75 kilograms, is resting on the floor. We have a coefficient of static friction of, I don't know, let's say 0.35. And then I want to know what is the minimum force needed to move the desk. Well, let's draw a diagram. It's always a good idea to draw a diagram. This is our beautiful desk. It's resting on the surface. There's gravitational force. There's normal force from the surface. It's being pushed by some force. And then the static frictional force always opposes the motion, or opposes the applied force. Okay, so in the y direction, we know that this thing isn't moving in the vertical direction, so the sum of the forces in the y direction is 0, and that's equal to normal force minus gravitational force. So we can see that our normal force is just equal to gravitational force in this case. The minimum force needed to move the desk, well, that means that in order to move the desk, that means that the force of the push has to be greater than the static frictional force. And we know that the maximum value of the static frictional force is equal to mu sub s times normal force. So, in order for the block to move, the pushing force has to be greater than mu sub s times normal force, which is equal to mu sub s times mg. So the pushing force has to be at least 0.35 times 75 times 9.8. And if I'm setting my calculator real quick, 0.35 times 75 times 9.8, that's 257.25 newtons. So if we get a force of just a hair over 257.75 newtons, the desk will start moving. Okay. So that's the kind of problem you typically see with static friction. But I could also throw a wrench in that. What if I said, instead of what is the minimum force needed to move the desk, I say I push with a force of 220 newtons. What is the static frictional force? Okay, you could embark on calculations, but we already know the maximum static frictional force is 257.25. Okay, and the static frictional force opposes any applied forces up to 257.25 newtons. Therefore, the static frictional force is going to be 220 newtons in the opposite direction. Okay, so keep an eye out for this kind of trick question. Static frictional force, remember, is equal to applied force up to a particular value. If we wanted to look at it, think of a graph here. We go applied force versus frictional force. As an object starts at rest, the applied force the frictional force is equal to the applied force up until we hit this value that is the maximum static frictional force. And then this is going to drop down to the, and this all the way here is static friction. And then once we apply enough force, the object will start moving, and then we have kinetic friction. Okay. And kinetic friction, I mentioned that it's easier to keep an object moving than it is to start an object moving. Quantitatively, what that means is that mu s is always greater than mu k. Always. It always takes more force to get that object moving than it does to keep that object moving. Right. And so as long as the object is moving, kinetic friction is equal to some value. The amount of force it takes to start that object moving is going to be greater than that, but static friction can take any value between 0 and that maximum static frictional force. Put an example conceptually here. So you have two blocks, block 1, block 2, okay, and they're resting on this surface, and somebody applies a force, and the object and these blocks, they start moving together with some velocity in that direction. And my question is, what kind of friction is present? Present. Take a second to think about that. Pause the video if you like. And, well, the answer is partially obvious. There's kinetic friction present because the objects are moving. And so there's that kinetic friction that will oppose the pushing force. But there is also static friction present. And that static friction is present between blocks 1 and 2. They're not moving relative to each other. So then at this interchange, there is a static frictional force. Okay? This is the static frictional force of block 1 on block 2 points that way, and then block 2 exerts a static frictional force on block 1 going the other direction. But there is static frictional force at this interchange where an object is not moving. Okay. Another question. We've got a car. Beautiful car. Car is moving along with some speed. What kind of friction? The tires are rolling. What kind of friction? Again, the answer seems like it would obviously be kinetic friction because the car is moving, right? But that's actually not the case. There is static friction between the tires and the road because there's only a single point of contact between the road and the tires. That point isn't sliding along. It's kind of being dropped down. And that might seem weird, but as long as the tire is just rolling and not the car isn't skidding, there is static friction because there's only that single point that's touching the ground, and that single point isn't sliding. There's just a new point that then is rolling down to hit the ground again. When you're walking, this is also static friction. You are moving, but you plant your foot on the floor, and it stays still while it's on the floor. Now, you might slip, and in that case, there would be kinetic friction. But when you're just walking along, that is also static friction between your foot and the floor. Even though you're moving, your foot is not sliding along the floor, and therefore there is not kinetic friction. Right? So keep in mind that different types of friction can be acting, and it isn't always obvious which type may be going on.